There are three equivalent ways to formulate quantum mechanics. Schrödinger gave us waves, Heisenberg gave us matrices. But Feynman asked a different question entirely. What if a particle doesn't take one path, but all paths simultaneously? Let's start with classical mechanics. A particle moving from point A to point B follows a path that minimizes the action. The action S is the integral of the Lagrangian kinetic minus potential energy along the path. Nature chooses the path of least action. But in quantum mechanics, we lose certainty. A particle doesn't have a definite trajectory. We can't say it took this path or that path. The wave function spreads, interferes, and defies our classical intuition. So how do we even think about paths? Feynman's insight was beautiful in its audacity. The particle takes every possible path, every conceivable trajectory from A to B, straight lines, loops, zigzags, even paths that go backward in time, they all contribute. This is the sum over histories. Each path contributes an amplitude, not a probability, but a complex number. For a path with action S, the amplitude is e to the power is over h bar. The imaginary unit I and the action in the exponent are what make quantum mechanics quantum. The propagator, the amplitude, to go from position xa at time ta to position xb at time tb, is the sum over all paths. We write this as an integral over all possible trajectories x of t, each weighted by e to the is over h bar. Here's the key: paths with similar actions have similar phases, so they add constructively. Paths with very different actions have random phases that cancel out. The classical path, where the action is stationary, is surrounded by paths that reinforce each other. As h bar goes to 0, the classical limit, the phase s over h bar oscillates wildly for any path except where the action is stationary. Only the classical path survives. The principle of least action emerges from quantum interference. Newton hides inside Feynman. Let's compute something concrete. For a free particle, the Lagrangian is just mx dot squared over 2. The path integral can be solved exactly. The propagator turns out to be a Gaussian. Square root of m over 2 pi I h bar t times e to the im times xb minus xa squared over 2 h bar t. This isn't just another way to write quantum mechanics, it's equivalent. The propagator satisfies the Schrödinger equation. If you know the wave function at time ta, convolving with the propagator gives you the wave function at any later time. Feynman and Schrödinger are two faces of the same coin. The path integral isn't just elegant, it's essential. In quantum field theory, we integrate over field configurations, not particle paths. Gauge theories, the standard model, quantum gravity, they're all formulated in the language of path integrals. Feynman gave us the vocabulary for modern physics. The path integral teaches us something profound. Nature computes the answer by trying everything. Every possibility contributes. The classical world emerges not because quantum paths don't exist, but because they interfere away, except where nature finds its optimum.